Well, good afternoon, good evening, good morning, whatever time it is in your part of the world. Welcome to the Exeter Web Seminar. We intend to discuss accurate failure data, the use of field-calibrated FMEDA results this afternoon. A few items of housekeeping. Audio should be coming out of your personal computer speakers. Let me just type a message for those who don't know this. Another item of housekeeping is that I'd like everyone to know to please do not hesitate to type in a question at any time using the Q&A tab above. In fact, let's give it a little test right now. I have a question. Can you hear the audio? How does it sound? Please type in an answer up in the Q&A box and we'll see how well that works. Number of people are answering already. Good. All right. Great. Thank you all. Not only did we test the audio, we tested the Q&A box. At least for a number of you, you have figured out exactly how to use the Q&A box. That's great. Thanks. My name is Bill Goebel. I've spent most of my professional career in new product development, so I've spent a lot of time in electronic hardware design, software design, and new product development. For the last 20 years, I've spent a lot of time studying reliability engineering and probabilistic analysis. Now, that is definitely the subject of our seminar this afternoon. And so we're going to have an enjoyable time talking about failure rate data. I work for a company called Exeter. Exeter is a global corporation with offices around the world. We have a number of people who come from new product development backgrounds, so we have a good, deep understanding of the instrumentation. We have a number of people coming from a safety certification background. We've hired a number of engineers who were even involved in the initial functional safety certifications. They've moved from one of the TUV companies into Exeter, and we have a number of people who have been involved with end-user applications. So I find that particular combination is particularly nice because we can all argue with each other and come up with some really nice solutions to problems. Exeter focuses on automation, safety, and reliability. And although it looks like we do a number of things, including consulting, certification, training, like this web seminar, engineering tools and references, and Exeter even administers the CFSE personnel certification program. All of our activities are focused on automation, safety, and reliability. Exeter publishes a number of reference volumes. In general, when we, rather than write up a company procedure on how to do something, we write a book, and we publish the book. And we make it available for everyone. Rather than create a database of failure rates and keep it secret, locked away in the company vault, we publish it and allow the information to be shared by everyone. I think it's a good idea for a couple of reasons. First of all, we're very much interested in any comments and criticism. And secondly, it makes the world a safer place. Those of you who are involved in functional safety know that there are two fundamental concepts: a set of detailed engineering processes to reduce systematic faults and design mistakes, and performance-based probabilistic design to reduce the probability of a random hardware failure impacting safety. The focus of our talk this afternoon is on the second part of this, the performance probabilistic analysis techniques. In the middle of the safety life cycle, when we have chosen our particular equipment, our level of redundancy, and our test methods, one can perform a reliability calculation to show if any given design meets the risk reduction criteria of the specification. That's the essence of the performance-based methodology. And I can honestly tell you, it was quite controversial when the standard was first written. And many of you know it remains quite controversial today. What do we need for this concept to work? We need high-quality failure rate data for both the products in which we have installed and new products which we are buying. This is an essential requirement of the performance-based probabilistic approach. When looking for failure rate data, when 61508 was first released in 2000, I found a lot of different data. And look at this particular chart for a pressure transmitter. I found a lot of different data that varied substantially from the lowest number here to the highest number, which is about 20 times higher. And I can see that these numbers vary by an order of magnitude, and that everybody else could see this too, and people began to think that the whole probabilistic concept could never work. Patrick DT OConnor, a well-known reliability engineer who wrote one of my favorite reliability engineering textbooks, wrote a letter to the IEEE Spectrum magazine in August of 2000. And it was a long letter, basically completely criticizing IEC 61508. And finally he said at the end, in particular, it requires quantification of risk probabilities. And I was thinking, as if risk probabilities were some huge three-headed monster that no one could ever face. Well, Dr. O'Connor, it's not that bad. It wasn't that bad then, and it's even better now. Saying that, however, does not change the fact that we have to answer some questions. If we look at all these sources of data, and here's another set on a solenoid valve, and this is even worse because there's several orders of magnitude difference here between the highest number and the lowest number. Which number is correct? Why do these numbers vary by orders of magnitude? I have one clue for you. The lowest number on this chart and on the previous chart was the result of manufacturer's warranty data. I used to work for a manufacturer, and a little later in the web seminar today, I will tell you what I was taught to assume. I'll tell you right now, given that set of assumptions, it's no wonder you get very optimistic, very low failure rate data. Field failure studies are, of course, the ultimate source of failure rate data. We must do top quality field failure studies. There's two kinds of data: owner-operator field failure studies and manufacturers' field return data studies. Now, each of these types have different kinds of data and different strengths and weaknesses. For owner-operator field failure study, there could be variations in the amount of data collected. I have found different definitions of what is a failure. Are wear-out failures included or not? I've seen many of these studies where they categorize broadly and merge different technologies, giving you results that aren't appropriate for any of the technologies. I've seen fault isolation often not complete, in other words, very poor root cause analysis. And data is available typically 10 years after a new product is introduced. It could be top quality data, but we're already talking about products in many fields that are obsolete. So it's got pluses and it's got minuses. Now, the manufacturer field return data have pluses and minuses also. Data analysis methods vary widely. Rarely is it understood what percentage of actual failures are returned to the manufacturer, and manufacturers have very different definitions of failures. That does not mean that both of these data sets are no good. In fact, both of these data sets have an amazing amount of useful information if you can go get it. After performing dozens of studies on owner-operator field failure, it's been recognized that the data collection process varies by an order of magnitude. A number of questions must be understood before one can determine the quality of a particular data set. When is a failure report written? What's the definition of failure? Are proof test results included? Are the as-found conditions recorded for a proof test? What are the operating conditions? What's the operating environment? And are systematic failures included? These are all very important variables in an owner-operator field failure data set. For example, one extensive set of test results indicated a product had an exceptionally low failure rate when compared to the Exeter Predictive Analytics benchmark. I'll explain what that is later. For now, just think of it as a number we use to determine data quality. When we see something that's too high or too low, we naturally ask questions. Why? An on-site visit to this particular test shop showed that when each instrument was returned for testing, it was cleaned up. And their definition of cleaned up is effectively an overhaul. It was disassembled, cleaned, replacement of seals and O-rings. In fact, I was surprised that any of the units failed after this particular refurbishment activity. Bottom line is, anyone who analyzes data must understand the test, prepare, and data collection process. As found conditions must be recorded. Obviously, they were not recorded in this case. In another set of data collected per a standard on data collection, ISO 14224, showed a failure rate much higher than FMEDA results. And after a discussion with the data analysts, they told me that they absolutely included all maintenance and operational errors in their data. Now, it is important that we have accurate probability of failure dangerous numbers. It is accurate that, and so we absolutely should include operational faults and random maintenance faults. But failures caused by bad procedures should absolutely be recorded and tracked, but they should be used to improve the procedures and to eliminate this systematic cause of a failure. Failures caused by random maintenance and operational errors should also be tracked and recorded, and they should be included in probabilistic analysis, but not as part of a product failure rate, as these failures are site-specific. I can tell you that one particular study that I was involved with found about a 3x difference in the failure rate of the exact same product from site to site. And it had everything to do with the maintenance capability, the maintenance training of that particular site. That's why I'm thinking that maintenance errors are site-specific, not product attributes. A very detailed study of a valve showed a very low failure rate when compared with the Exeter Predictive Analytic benchmark. The conclusion made by that manufacturer who commissioned the study was that this valve would be an excellent choice for safety applications as well as the control applications for which it was designed. Now, the fact is, this particular valve was absolutely designed and sold as a control valve. Nowhere in the analysis report did it ever say where the failure data came from. Was it a control application or a safety application? In a control application, a mechanical product is somewhat dynamic. It's moving. In a low-demand safety application, such mechanical products may be static, motionless, for perhaps years. Then, the failure rates will be much different. The failure rates will be higher. The failure modes will be much different. There'll be cold welding. There'll be stiction. There'll be all kinds of modes in static applications that didn't even exist in a dynamic application. So, lesson learned, application conditions, including static versus dynamic, must be recorded and listed in any analysis report. Now, that doesn't mean there isn't a lot of good data out there. In fact, in all these cases, when the process was reviewed and cleaned up, when as-found conditions were recorded, the data collection, or the data set, the data collection process was significantly improved, and the resulting data was significantly improved. What about manufacturers' data studies? When I worked for a manufacturer, I was taught to calculate operational hours based on shipping records. And we assumed, of course, that we shipped the product and it was hooked up and connected within a week. We also assumed, of course, all failures are returned, because why wouldn't somebody return it to us? Well, the answer is it costs money as the first reason, and people are busy, and there's dozens of other reasons. The bottom line is manufacturers have no idea how many of the actual failures are being returned. Many manufacturers have a process where a returned unit is tested by a technician, perhaps on a bench. And if the technician doesn't find anything wrong, they're marked, no problem found, therefore not a failure. Hey, you're not even close to the operational conditions of the field. Maybe it fails in the field, but doesn't fail on the bench. Those are all things that make this particular data set questionable for calculating absolute failure rates. However, the beauty of this is when a real failure is found, the root cause analysis is done well. Most manufacturers trace the cause of a problem back to the specific component and the failure mode of the component. So this data is not necessarily useful for calculating absolute failure rates, but it is useful for determining failure modes of components. It's very valuable for that. Manufacturers' data is also valuable, is becoming much more valuable, I should say, as a result of some new technology. Many products today have built-in power-on hours counters. when a product comes back from the field, you can interrogate the memory and discover how long this product has been in operation. In many cases, the exact number of operational hours. That is the metric time to failure, the primary random variable of reliability engineering. It's a tremendously valuable number to get a collection of TTF numbers for a particular product. That's an excellent way to directly calculate the failure rate, but what you get is an upper bound, a high number, because you're not taking into account all the units that are successfully operating in the field. Eventually, you'll get enough data to come up with a pretty good overall failure rate, but of course by then the product's obsolete and out of production. But even the early TTF numbers are valuable as an upper bound. You can also calculate a lower bound by taking a look at the warranty period only. You count only the failures during the warranty period and the operational hours during the warranty period. You assume a percentage of units returned which are significantly below 100%, depending on the cost of the product, and you can calculate a lower bound, lambda. And sometimes it's quite surprising that the difference between the upper bound and lower bound are not that far apart. So there's a lot of valuable information in this data if you know where to go get it. Even so, with all that data, we need more. I need a way to calculate failure rates of new instruments. Hence, the failure mode effect and diagnostic analysis technique. I'm just checking here to make sure, but I don't see any questions yet. By the way, comments are appreciated. If you think I say something that doesn't make sense, spit out a challenge. It's okay. Type out a challenge, I should say. The concept in a failure mode and effect analysis is an old concept. It's been around since the early days of reliability engineering. Rather than keep statistics on a product which may have hundreds of components, can't you break those statistics down into the components and keep statistics on the components themselves? Then if a new design comes along using the same components, you can use the technique of simply analyzing the reliability network of the product. For the most part, it's a series system where any component fails, the product fails, and generate a failure rate for a brand new design. It's the same concept used in the old Mill Handbook 217, which was created about 40 years ago. Therefore, using a component database with failure rates and failure modes for all the components used, you can go through this FMEDA process and come up with a product failure rate, the product failure modes, and the diagnostic coverage factors. That's the difference between the old techniques and the new. An FMEDA looks at any onboard diagnostics, the impact of those diagnostics, and generates failure rates specifically applicable for safety system analysis. Sometimes, in fact, it's essential that the various assumptions during the FMEDA are verified by testing, and most FMEDAs are backed up with a very detailed fault injection test on a particular product. So FMEDA is not just a theoretical calculation, it's a calculation backed up by testing. Now, what's the problem with FMEDA? The accuracy of the result depends on the accuracy of the component database. When you look at this picture, I hope that becomes self-evident. So what do we do about the component database accuracy? The answer is the component database must be based on and calibrated by a strong set of field failure data. The field failure data generates the component database, which is used in an FMEDA analysis. And frequently then, FMEDA results are compared with field failure data, and if there's any fundamental difference, the reason must be ascertained. I'm pleased to say that after over 100 field failure studies of both end-user and manufacturer data sets, representing more than 10 billion unit operating hours, Exida has constantly updated our component failure database to improve the model and to identify differences between the model and results. Got a question? What is the relationship or impact between validated failure rates and systematic constraints introduced in 61508? Actually, there is a relationship, but if we can hold up, I have some slides coming in just a little bit where I can answer that. The component database has what I call hierarchical FMEDAs as well as field failure data. What do I mean hierarchical FMEDAs? Sometimes what most of us call a component actually consists of 10 to 1,000 components at a more detailed level. For example, a relay. There might be 10 to 20 components in there. You've got the coil, different coil types with different insulation, different kinds of magnetic coupling with failure modes of residual magnetism, contacts, springs. A detailed study of the components of the relay results in failure rates and failure mode for the relay component, which then goes into the component database, which then is used for an FMEDA for a product level, like a gas detector with a relay output. Microprocessors and complex integrated circuits are also examples of where hierarchical FMEDAs are important. These components have very complex failure modes and failure rates, which depends very much on the internal design of that component. And so FMEDAs are being done at the integrated circuit level. For example, there are microprocessors being designed today for functional safety. They have features like duplicate memory with internal comparison. They have dual CPUs with diverse substrates, automatic self-diagnostics in hardware based for the registers, instruction decoders, cache, I/O chips, and so forth. Some of these are so thoroughly and carefully designed that the dangerous undetected failure rate of the microprocessor has gotten down in the range of 2 times 10 to the minus 9 failures per hour. Whereas a typical microprocessor might be sitting in the range of 60 times 10 to the minus 9 failures per hour. These particular components and the FMEDA results on such components also go into the component database, both in specific model number form and in generic form. Now, given that you know that the component database is so important to this FMEDA or modified FMEA process, you need to know that all FMEDA results are not alike. Take a look at some of the results on this chart. For a ball valve, we have an extremely low number and we have a high number. And you can see it depends on both application conditions when specified, and of course, other than that, we're not sure why there's over an order of magnitude difference here. The same thing on actuators. Here's an example for a rack and pinion actuator compared to a double acting rack and pin actuator from an Exida FMEDA, the highest number. That's a pretty big difference. Why do you think those numbers are so different? Okay, I have a clue. As we said before, be very wary of any technique based on manufacturer's warranty data. You heard what I was taught. I can't imagine it's very different in other manufacturers. These particular results are dangerously optimistic. We can also compare FMEDA results with a number of public field failure studies. If we compare typical FMEDA results with failure rates in the range of 3.5 to 8 times 10 to the minus 7 with plant studies from the chemical industry, we see we're right in the exact correct range. Even older failure studies are not that far out. It is interesting when I sit down and compare FMEDA results that the total failure rate on old transmitters and new transmitters is roughly the same. Why does that make any sense? Well, because the designs are roughly the same. One thing that is very different, however, is the dangerous undetected failure rate. Does that make sense? Well, these newer products that are safety certified have extensive online diagnostics that convert otherwise dangerous failures into detected failures. And you can see that the dangerous undetected failure rate on some of these old products, like 2.87 times e to the minus 7, is very different by an order of magnitude than the newer products, which are sitting at more like 2.8 times 10 to the minus 8 failures per hour. That's the direct result of new technology and why it's so important to predict the dangerous undetected failure rate as compared to the total failure rate. But never compare total failure rate to the dangerous undetected in an FMEDA. That makes no sense. When scanning failure rate data from many different sources, most are in the correct range from an FMEDA. There are some, like the ARETA database, where the ARETA failure rates are much higher than FMEDA data. We do need to sort through that and find out exactly why. But right now, just remember that ARETA data says FMEDA is too low. The Nemore study, on the other hand, came out that the Exida FMEDA data was slightly pessimistic for sensors, slightly pessimistic for logic solvers, but very pessimistic for final elements, solenoid valves, actuators, valves. The Nemore study indicates that FMEDA data is very high. So I think that's a good position to be in, where one set of field failure rate data says you're too high and another set says you're too low. Obviously, in the end, we'd like to get to the bottom of all this, but when we asked, we were told the Nemore data was confidential, and anybody outside the contributing companies could not have any look at the data. So we'll probably not be able to resolve this one. There are certain things that are absolutely not included in FMEDA results that everyone must understand. Maintenance-induced failures are not included. This is primarily because they are site-specific and not product-specific. I don't want to diminish the value of having site-specific maintenance-induced failure data, And that's the extremely valuable thing, an extremely valuable thing we can get from field failure data collection. Now, I will say that in the Excellentia tool has a maintenance capability parameter that adjusts many parameters, including probability of repair, probability of failure, according to maintenance capability. And that is, in my view, an excellent way to deal with site-specific variations in PFD data. FMEDAs do not include systematic failures. And if you read the 61508 definition, you can summarize it in my head by saying failures due to design or procedure errors. Now, systematic failures should be tracked. They are an important part of any good field failure data collection system. But the primary reason for tracking a systematic error is so one can do a root cause analysis, finding out why there was a systematic failure, and take corrective action. That's how a good field failure data collection system can significantly improve productivity of a plant. But these are not product attributes that should be reflected in product failure rates. I'll double check my questions one more time. Nothing. All right. Wear-out failures are not part of FMEDA data. The FMEDA data produces a constant failure rate, which has value during the useful life. In general, that failure rate should be somewhat conservative. In other words, higher than real reality. Instead, FMEDAs produce a useful life parameter, which is the time period for which the failure rate data is good, and the intent, as specified in functional safety standards, is when a product reaches its end of useful life, you need to replace it or refurbish it. In the previous version of this seminar, I was asked, well, don't failure rates change as a function of operational environment? And the answer is absolutely yes. That's why FMEDAs must be done on a particular set of operational parameters. From using a number of international standards, which classify operating conditions, and I'm talking temperature change, electrical stress, chemical stress, mechanical stress, shock and vibration. There are standards for all of these stress variables. And they can be grouped according to environmental expected outcomes. Right now, the FMEDA results can be done for control room cabinets, field equipment with two-wire devices. Why two-wire devices? They have very low power dissipation, and there's very little internal self-heating. Four-wire field equipment, some of which dissipate 10 or 20 watts, in which case you get a pretty high temperature differential between the outside ambient temperature and inside the case. We do have an automotive operational profile. And recently we've added a subsea and an offshore topside operational profile. So any manufacturer can have an FMEDA done per one or more of these different operational profiles. The failure rates will be different. Ironically, for some equipment, subsea environment, which sounds pretty bad to me, produces a lower failure rate because the temperature is so much lower. You can imagine any component where the temperature rate or failure rate goes up with temperature will have a lower failure rate with lower temperature. Earlier I talked about exit of predictive analytics. The concept is use all the information available to generate the best failure rate data available. What information is available? design details. An FMEDA analysis shows the design details. We know exactly what components are used. We know exactly what design margins are being used. We've done fault injection testing to show what diagnostics are present. If someone does enough FMEDAs, eventually you get a pretty clear picture of what the failure rates for a particular product category should be as a function of operational profile. And given a large number of FMEDAs from the best design to the worst design, we can accumulate the results and predict a failure rate range, upper bound, lower bound. We can predict failure modes, and we can predict a useful life range. That information for any particular product category then can be used to compare the results of field failure analysis. And if it turns out there's some significant difference between the data from a field failure set and the predictive analytic benchmark, a red flag goes up. There is a reason to ask questions. What is your definition of failure? Are you recording as found conditions and so forth? So the predictive analytic model is very useful for predicting the quality of a set of data. I see a question, but nothing is popping up on the screen. Okay, there it is. How is process severity handled in an FMEDA in a chemical plant? Field equipment is a benign application assumed by the manufacturer. Good question. In the operational profile, one of the variables is corrosion, atmospheric corrosion. So if you're talking about corrosive chemicals in a chemical plant, that is considered in the operational profile. If in fact you are talking about materials compatibility between process wetted parts and the instruments, that is not covered. That is absolutely not covered. Instead, what is covered is, well, there's a statement that materials must be checked for compatibility. Now, if a design engineer at the site makes a mistake and doesn't check for materials compatibility, or doesn't know about materials incompatibility, then those failures it's important that those failures be recorded and that corrective action be taken in that materials need to be changed to compatible materials. So far, we haven't found a way, because we believe this is a site-specific failure rate. We don't think it's product-specific. We haven't come up with anything better for now. So the assumption is materials are compatible with process chemicals. The beauty of this predictive analytic benchmark is it can absolutely be used to judge the quality of field failure data. Not that there's a problem with the data, but there's a challenge to the data. And if the questions are answered well, then something's wrong with the predictive analytic model, or something's wrong with the field failure data set. The important thing is to find out what the difference is and why, and make adjustments. IEC 61508, the new version 2010, does talk about data quality. It's in a section of the standard called Route 2H, and in fact, you may eliminate architectural constraints based on 90% confidence of having quality data. Now, there are paragraphs that indicate 90% confidence is much more than just taking a 90% confidence interval in your statistical data analysis. It's a matter of judgment regarding the quality of the data collection system. So don't think it's just a statistical issue. You really have to have a good, high-quality data collection system. But the reward is, if you do, you will have good data that will typically allow the PFD calculation to be the limiting factor when you do your SIL verification. To check this out, Exeter did a study of over 50,000 SIF designs in the Exeter database. 70% of them, the limiting factor from the PFD calculation and the architecture constraints was the same SIL level, indicating architecture constraints were simply not necessary in 70% of the cases. And 15, the PFD limited the SIL more than the architecture constraints, again indicating that we're up to 85% of the time we didn't even need to be looking at architecture constraints, which are minimum levels of redundancy. However, 15% of the time, the architecture constraints limited the SIL level, which indicates maybe we better keep the architecture constraints. So we dug a little deeper. Approximately 95% of these 50,000 SIFs used the Excellentia SERH failure data, which is primarily based on field-calibrated FMEDA results. Approximately 5% used my own failure rate data. We started digging and discovered that many of those failure rates were entered based on cycle testing and other high-demand, continuous demand applications, where the people involved in the analysis just did not understand that you cannot use that information for low-demand applications. That was roughly 5% of the total. We also found that the other 10% of architecture limitations were due to relatively short proof test intervals where the PFD went down, but the architecture constraint did not. Now, I was thinking about this, and I'm thinking, gee, if you're realistic, if you really do proof tests effectively and frequently, why shouldn't you get credit for it? Why should you design in extra equipment when you're doing proof testing? In my mind, I just don't see a reason for it. So the bottom line is that 95% of the time, the PFD calculation gave the correct SIL verification result. To me, that's very strong evidence of high quality data. That doesn't mean we need to do better in the future. As we all move forward, the advantages of high quality field data collection will become more and more apparent. In my mind, especially for maintenance-induced failures and systematic failures. Given that these are very site-specific, it's very important that a site implement a good, high-quality field data collection system. Fortunately, there are new tools available to make this much easier than it ever was in the past. You don't have to go through 2 years of having a consultant set up an SAP database. These new tools will work just fine. And more important, analysis services are available using Exeter Predictive Analytics, and data output reports are compatible with the Process Equipment Reliability Database from AICAG. I look forward to the future where we get better failure data. No doubt, the calibration of FMEDA components will improve, especially identifying unknown failure modes and other things that are currently being missed right now. I'd like to ask that if anybody has any further questions, please type them in. If you have a question tomorrow, next week, please do not hesitate to send me an email. If you have any comments, please do not hesitate to send me an email. I'll answer them asynchronously, and it might take several days to get back to you. But I do my best to get everything answered. If you have any other questions right now, please ask. Okay. We'll get back. Let's verify that we answered the one question. What's the relationship or impact between validated failure rates and systematic capabilities? Well, the bottom line is, if you have high quality data, which is what I assume you mean by validated failure rates. The 2010 version of 61508 allows you to not include architecture constraints. And if you have high quality data, you don't have to put in redundant components unless your PFD calculations say that you must. The fact is, I don't want to be too optimistic here, this is not a loophole to go reduce your designs. In fact, your PFD calculations 95% of the time will tell you you must add redundancy. I hope that answers the questions. If anybody else has any more, please don't hesitate to type them in. See if anything else comes up on the screen. Make sure I have them all. All right, it doesn't look like anybody else has any right now. Let me just wrap up by saying thank you very much for attending. If you have any questions tomorrow or next week, please send them. Meanwhile, thank you very much. Stay tuned for next week's web seminar. Goodbye.